morning, and this is being my first lecture. I would like to welcome you to this workshop. Today I will be talking about fluid statics. Now, yesterday you have studied the concept of a continuum, and you will find that many of the concepts of fluid mechanics are treated nicely in books on continuum mechanics. Okay, so, under continuum mechanics you can study solid mechanics. Defective and you have fluid mechanics. এইভাবে তো আমি পড়াতে পারবো না, এ কি এটা তো যোগ হয়ে গেল একটা। Now, under fluid mechanics you can study fluid statics.
slowly press করে লিখুন, press করে লিখুন। slowly press করে লিখুন হবে। এটা করে এটা
So, just as mechanics can be studied separately under the head of statics and dynamics, we can study fluid statics and fluid dynamics. So, today we will start with fluid statics, and you will find that many of the concepts of fluid statics will be required for your study of fluid dynamics. So, first of all we will try to find what is the stress distribution in a fluid at rest. So, we will look at stress Now, let us consider an element of fluid which is in the form of a rectangle. And let us say you have a point P. So, we will show the coordinate system. Let us say we consider a two dimensional situation, this is x, this is y, and we have taken an element whose surfaces are parallel to the coordinate axis. Now, we want to find stress at a point. Let us say we want to find the stress at this point P. So, if we divide this fluid element into two parts by a vertical plane, and we call the left side 1 and the right side 2. Okay. Now, the molecules on this side 2 will exert a net force on the fluid which is in this left side of this vertical line, which we are calling 1. So, let us show that using a free body diagram. So, if this is the element 1, okay, and we will show separately the free body diagram of this 2. Now, this point P will appear in both the figures. What we have done is we have an imaginary plane here which is dividing this rectangular element into two halves. Now, let us say the net force exerted by 2 on 1 through this surface is in this direction, let us say. We can call it delta F S 1 2. So, this subscript S indicates that it is a surface force exerted through this surface, and 1 2 means it is a force on the fluid in 1 exerted by the fluid in 2. So, this is the net effect of the intermolecular forces. Now, this area element we will call delta A x, the area of this surface which is the same as the area of this surface. The subscript x indicates that this surface is perpendicular to the x direction. Now, this is a vector. So, I will indicate vectors by over bars. Now, this has two components. So, you can write it as the sum of this component, the x component and the y component. So, one can write delta f s one 2 vector as delta f s, I will call it x I. So, this is the x component of the force, and delta f s y j. Now, I is the unit vector in the x direction, which has magnitude 1, and j is the unit vector in the y direction, which has magnitude 1. Now, we can define stress you can define a stress vector you can call it capital S, and on the I plane. Now, we can go back to this figure. So, by I plane I mean this plane whose unit normal is in the I direction. So, this we can write as delta f s 1 2 vector by the area So, this gives the intensity of the force, and the units will be newtons per meter square. So, this is the average stress on that plane. Now, if I take the limit delta A x going to 0, this defines the stress at the point P on a plane which is perpendicular to the x direction. Now, we have considered a two dimensional situation. So, this force has two components, and we can write it as delta f s x I, and we are dividing it by delta A x. And the other term will be delta f s y by delta A x j, and you can put the limit. So, the first one we will call sigma x x, and the second term we will call tau y x, sorry, tau x y. So, here the notation is that the first subscript denotes the plane. So, we are considering a plane whose outward normal is I. So, it is perpendicular to the x direction. So, the first subscript on these two quantities is x, and the second subscript gives you the direction of the force. This is the force component in the x direction, and this is the force component in the y direction. Now, if you go back, now, when a fluid is at rest, the shear stresses are going to be 0. You have studied the definition of a fluid, that if you have a shear stress, even if it is infinitesimally small, the fluid will start to deform, and it will deform continuously, which means that it cannot be at rest. So, when the fluid is at rest, you are going to have S on the I plane equal to sigma x x I. The other components are 0. So, if we go back to that figure, this was the element. This is the direction of the stress. So, if sigma x is positive, it will be perpendicular to this direction and outward. Now, this was what we called 1. Okay. Now, if you look at the free body diagram of the part which we had called 2, now these are internal forces. So, if we add the 2, it should cancel out. So, if the stress on this plane at the point P is in this direction, at the same point P here, it will be in the opposite direction. So, you have S, this is the vector S vector at the same point and on the minus I plane will be minus sigma x x I. So, this is the sigma x x. So, this sigma x x and this sigma x x, they are going to be the same, because the point is the same and these are internal forces, but they must be in opposite directions. So, the if you add this force and this force together, the net force is 0, because these are internal forces. So, this you can view as a statement of Newton's third law. So, I can write this as minus S of I. Okay. So, we see that if sigma x x is positive on the plane whose outward normal is I, it is pointing in the positive I direction, and at the same point on the same plane, but if you are looking at a plane here, this side of the plane whose outward normal is minus I, then the sigma x x is in the negative direction. So, this gives you the sign convention for stress. Now, let us consider a fluid element. And we have a point on this face and a point on this face now. Okay. And again we are taking a rectangular element whose surfaces are parallel to the x and y axis. এইভাবে কি পড়ানো যায়? So, let us say this is sigma x x at this point, which we are calling P, and if I call this point Q, the stress will be in this direction. So, we have discussed the sign convention of the stresses, but the stresses can vary from point to point. So, this sigma and this sigma need not be the same. So, what I have shown here are the directions of sigma when sigma x x is positive. Now, you see that when sigma x is positive, the forces are, or the stresses you can see, are tensile in nature, because they try to pull these two surfaces apart. Now, I will draw another case where it is negative. So, at this point P, suppose the stress is negative, then this will be the direction. And at the point Q also, if it is negative, the arrows will point in the opposite direction. So, this is your sigma x x if I call this point q, this is sigma x x of q. So, this is the case when sigma x x is negative. Now, you see that the stresses are compressive in nature, because they want to push these two surfaces in. So, this is a tensile stress, and this is compressive. Now, as I mentioned, there are many features of solid mechanics and fluid mechanics which are common. The concept of stress is similar in any continuum material, whether it is a solid or a fluid, but when the fluid is at rest you cannot have a tensile stress. The stresses are always compressive, whereas for a solid it can be either positive or negative. So, it could be either tensile or compressive. Now, we will consider a fluid element which is a wedge. So, if this is the x direction, this is the y direction. This is the origin. So, this wedge has three surfaces. This one is O A, I can call this O B, and you have an inclined surface which is A B. Now, this inclined surface is characterized by the outward normal, which I will call N. So, we will look at the equilibrium of this fluid element and find a relation between the stresses on this inclined plane and the stresses on these two planes which are perpendicular to the x and y directions. Now, if I say this angle is theta, okay, I can draw here the horizontal and vertical lines. This angle being an alternate angle is going to be theta, then this angle will be 90 minus theta, and this angle will be theta. So, this vector n I can write as n x I plus n y j. It has two components. Now, I can see that n x is this, which is sin theta, and n y is cos theta. The magnitude of this vector n is 1, because it is a unit vector. So, I am using this hat sign or caret sign to denote unit vectors. So, if you look at the magnitude of n, that is under root of n x squared plus n y squared, that is equal to 1. Now, let us show the forces. Since the fluid is at rest, the shear stresses are 0. So, the stress here is going to be in this direction, normal to this. The stress here is going to be in this direction, and the stress here is going to be in this direction. So, this is sigma y y, this is sigma x x, and this we can call sigma n n. And let us say the gravity vector is in this direction. Now, let us consider the equilibrium of this element. So, if you look at this is at rest. So, the acceleration is 0, hence the sum of forces in the x direction will be 0. Now, the sum of the forces is minus sigma x x into A x, where A x is the area of this face perpendicular to the x direction. And then here you have this force component. So, this angle you know is theta. So, it is going to be plus sigma n n into, let us say, A n is the area of the inclined face. Now, you want this component. So, that is multiplied by sin theta. So, this is equal to 0. Now, A x is the length of O b into, we can take unit depth in the z direction, and similarly A n is the length of A b into 1. Now, you can see from this figure that if I take A b sin theta, that is O b. So, A n sin theta is nothing but A x. Okay. So, this quantity and this quantity, they are the same. So, this equation tells you that sigma n n is equal to sigma x x. Now, we will look at the force balance in the y direction. So, if you look at the sum of forces in the y direction, this is x and this is y, you are going to have this component of the force, this angle was theta, this is sigma n n, this is sigma y y. This force will not play a role in the y component balance. So, this is going to be sigma n n A n, this is the force, sigma n n is the intensity of the force multiplied by the area gives you the force in this direction. You want the vertical component. So, here that is going to be cos theta, and here you have minus sigma y y into A y. So, these two are the surface forces. Now, you also have a body force because the gravity is in this direction. Okay. So, you are going to have minus the mass of the fluid inside this wedge into g, and this is going to be equal to 0. Now, this mass is the density into the volume. And once again you can see that if this is A n, your A n cos theta is equal to A y. So, this quantity here A n cos theta is going to be the same as A y. So, if we divide by this A y, you are going to have sigma n n equal to sigma y y plus rho the density into g into the volume by this area. Now, consider a wedge which is very small. So, we consider the limit when the volume goes to 0. You have defect here. Huh? So, this was one wedge. Consider another wedge of a smaller direction, but the inclined surface is the orientation is the same. So, we consider a sequence of wedges. This is the point O, with lesser and lesser volume, but they are all self similar. So, the direction of the forces is the same. Now, what will happen is that the volume will go to 0, A y also goes to 0. But the volume goes to 0 faster than the area. So, V by A y, this will also go to 0. So, if we go back to the previous equation, this quantity will go to 0, and in the limit you are going to have sigma n n equal to sigma y y. So, we have this relation that sigma x x equal to sigma y y equal to sigma n n. Now, we consider the case where the y direction was vertical and x direction is any horizontal direction. So, the z direction is also horizontal and you can rotate the coordinate system and make the z and the y identical. So, you can say that this is also equal to sigma x x z z. So, finally, we have this result that sigma x x equal to sigma y y equal to sigma z z equal to sigma n n. That means, at a point the normal stress is the same in all directions, and we have seen that a fluid cannot sustain tension. So, these quantities are going to be negative according to our sign convention. So, that magnitude is what we call pressure. So, we will say that this is equal to minus of P, where P is the pressure at the point O, and the point O could be anywhere. So, at each and every point you have only normal stresses and they are all equal. So, the force per unit area is the same in all directions, and if you look at the shear stresses, you are going to have tau x y equal to 0. Similarly, you are going to have tau y x also equal to 0, you are going to have tau y z equal to 0 and tau z y equal to 0. Tau z x equal to 0, tau x z equal to 0. So, the shear stress on any plane is 0 and the normal stress has the same magnitude at a given point, but of course, it can vary from point to point. So, this P at two different points will be different in general. So, now we have defined the concept of pressure at a point. So, we will talk about now what is called the pressure field. So, this is a function, we will call it p of x, y, z, and we have a pressure field in fluid dynamics also, where it can be a function of time. Now, in fluid statics, of course, it will be not depend on time, because it is at rest. So, this is a function which tells you how the pressure varies with x, y, z. So, if you want the pressure at a point, all you have to do is substitute the coordinates of the point in this function, and that will give you the pressure at that point. Now, this function you will have to find by solving equations. So, next what we will do is, all right, now let us look at the equilibrium of a fluid element. So, now what you are going to have is the sum of the forces will be equal to 0, because there is no acceleration. Now, there are two kinds of forces, one is the surface force. So, we can say is F s plus F b equal to 0. So, we need to find an expression for the surface force on a fluid element. So, let us go back and look at a rectangular element of fluid. Fluid is at rest. So, we know that the force on the surface is due to pressure, which is compressive in nature. So, this will point this way and this will point this way. Now, these two magnitudes need not be the same in general. If they are the same, then the forces will cancel out and the net surface force on this element may be 0. Now, we are considering a general pressure field. So, the pressure at this point and the pressure at this point, they are going to be different. So, if I call this R, a left point L and the right point R, if you look at the net surface force on this element in the x direction, this is going to be the difference of the two pressures P L minus P R into the area element perpendicular to the x direction. Now, as you can see, if these two pressures are the same, then the net force will be 0, and that could be the case, but we want an equation which can derive describe the flow for any arbitrary case. So, this is the point which we are calling R, and this is the point we are calling L. Now, let us say this distance is delta x. Now, P at the point L, which we are calling P L, is obtained by taking the pressure field and putting the coordinates of the point L, which is x L, y L, z L. Now, P at the point R will be P at x R, y R, z R. Now, x R is x L plus delta x, whereas y L is the same and z L is also the same. So, we can call it P of x L plus delta x y L z L. Now, in continuum mechanics these functions are continuous functions. So, it can be expanded in a Taylor series about the point x L, y L, z L. So, this we can write as P of x L, y L, z L plus del P del x x L, y L, z L into delta x plus I will say dot dot dot, these are higher order terms. Now, you will notice that this quantity here is your P L. So, essentially what we have is P R equal to P L plus del P del x at the point L into delta x plus higher order terms. Now, what we wanted was P L minus P R. So, if I move this term to the right hand side and this terms to the left hand side, P L minus P R will be equal to minus del P del x into delta x. So, what you see is that if the pressure does not vary in the x direction, then the net force due to pressure on this fluid element will be 0, because they are in opposite directions and the magnitude is the same and it will cancel out. Now, the net surface force F S net in the x direction we said was P L minus P R into A x, which is P L minus P R into delta y into delta z, and P L minus P R we showed was minus del P del x delta x. So, this quantity is P L minus P R multiplied by delta y delta z. So, we see that this is minus del P del x into delta v. Where delta v is the volume. So, if you look at F s net x by the volume, that is minus del P del x. Of course, there were higher order terms which we did not consider, but this expression will be exact if you take the limit delta v going to 0. So, now if you write it in vector form, F s net it will have a component F s net x into I plus F s net y into j plus F s net z into k. This is going to be minus del P del x into, you can call it delta V I, and similarly this will be minus del P del y delta V into j. This is going to be minus del P del z delta V into k. So, if you look at F s vector net by the volume, you are going to have minus del P del x I can factor out the minus sign plus del P del y j plus del P del z k. And of course, there are higher order terms. So, this is true only in the limit delta v going to 0. So, this I can write as minus grad of del of p, or I can write it as minus grad of p. Now, if you look at the body force F b, that is simply for our case the body force due to gravity. Now, you could have other kinds of body forces also, but we are not considering it in this course. So, that is simply the mass into the gravity vector. So, this we can write as the density into the volume into g. Okay. So, now if you look at the sum of the forces on the fluid element, you are going to have the F s net, the net surface force, and you are going to have the body force. So, this you can write as minus grad of P delta V plus rho delta V into g. So, if you factor out the delta V, you have minus grad P plus rho g into delta V. So, this must be equal to the 0 vector, and this holds for all arbitrary delta V's. We can divide by delta V, and we have this relation then that minus grad P plus rho g equal to 0. Now, you can give a physical interpretation. The first term is the net pressure force per unit volume on the fluid particle, and this is the net body force per unit volume in the fluid particle. So, this holds at each and every point. So, this you can also write as grad P is equal to rho g. So, this is what we call the basic equation of fluid statics. আচ্ছা এই দাগটা কেন হলো, এখানে তো কিছু নেই। Now, we will try to find the pressure distribution. Now, the gravity vector I can write as g x I plus g y j. Now, the components g x, g y, g z will depend on the choice of the coordinate system. Okay. Now, if you start with this equation grad p equal to rho g, this is a vector equation. If you look at its x component, you are going to have del p del x equal to rho g x. Then if you look at the y component, you are going to have del p del y is equal to rho g y, and if you look at the z component, you are going to have del p del z is equal to rho into g z. So, these are the three equations which you have to solve. Now, let us start with the first equation. Now, we will do it for the case when the density is constant and g x, g y, g z there are anyway constants. So, you have del p del x equal to a constant which is given by g x. Now, if we integrate this, you are going to have p equal to rho into g x, this constant multiplied by x plus some function, we can call it f 1 of y and z. Since this is a partial derivative, we have this function of y and z. If you take this expression and differentiate it partially with respect to x, this del del x of f 1 is going to be 0 and you are going to get back this quantity. Now, we need to find this function f 1. This function we can find from the other two equations. So, let us look at what is del p del y from this expression. Now, this being x, the first term will be 0 and you are going to get del of f 1 del y, and this we know is rho into g y. So, if I integrate this equation, I am going to get f 1 is equal to rho into g y into y plus something we will call f 2 of z. Again, if I take this equation and differentiate partially with respect to y, the derivative of this term will be 0 and derivative of y with respect to y is 1, and you will get back del p del y, which is del f 1 del y equal to rho g y. Now, our goal is to find this function f 2. So, let us look at, let us first of all substitute this over here, we will get p is equal to rho g x x plus rho g y y plus f 2 of z. Now, let us look at the third equation del p del z. This will be d f 2 d z, which is going to be equal to rho times g z. So, if I integrate this, you are going to get f 2 is equal to rho g z, which is a constant, multiplied by z plus, now this is going to be a constant of integration because this is a total derivative. So, if I take this expression on f 2 and substitute into the expression for p, we are going to get p is equal to rho into g x into x plus rho into g y into y plus rho into g z into z plus c. So, for any coordinate system, when the density is constant and the fluid is at rest, this gives you the expression for P of x y z. Now, I will show you another way to get this. If you look at dP, you can write dP as del p del x dx plus del p del y dy plus del p del z dz. This we can write as rho g x dx plus rho g y dy plus rho g z dz. So, this I can write as d of, since rho and g x are constants, g x x plus rho g y y plus rho g z z. Or we can write it as d of p minus rho g x x plus rho g y y plus rho g z z is equal to 0. That means, P minus rho g x x plus g y y plus g z z will be equal to some constant if I integrate this. Now, this I can also write in a compact form as p minus rho g dot r equal to constant, or you can say p is rho g dot r plus c. So, here r is the position vector of a point and g is the gravity vector. So, r is x I plus y j plus z k. Now, let us choose a coordinate system where the z axis is vertical. So, this is x, this is y and this is z. So, this is the direction of gravity, let us say. So, you see that G now is minus G k. That means that the x component of G is 0, y component of G is 0 and the z component of G is minus G. So, if you look at G dot r, that is G x x plus G y y plus G z z. Now, this term is 0, this term is 0 and G z is minus G. So, you have minus G z. Okay. So, with reference to this coordinate system, P will be minus rho G z plus a constant. So, this expression gives you the pressure distribution under the following conditions. One is the fluid is at rest, then density rho is a constant and z is vertical and pointing upwards. If you use any other coordinate system, then this equation will not be valid, even if the fluid is at rest and the density is constant. Now, suppose I take z to be vertical and pointing downwards, then this would have been plus rho G z plus a constant. The previous expression which we wrote is general and valid for any coordinate system. Now, the last expression you could have derived directly also, when you have the z axis vertical and G is downwards, you have del p del x equal to rho G x equal to 0. Then you have del p del y equal to rho G y which is equal to 0 and del p del z is equal to rho G z which is minus rho G with reference to this coordinate system. Now, the first two equations tell you that P does not vary with x and P does not vary with y. So, that means this is a total derivative which is dP dz is equal to minus rho G. There is a difference from a mathematical point of view between this equation and this equation. This equation, if you integrate, you will get P is equal to minus rho G z plus a constant of integration, whereas if you take this equation and integrate, you will get P equal to minus rho G z plus a function of y and z, which you have to determine from these two equations. Okay, now let us take a break for half an hour, then we will be back.